Hello everyone, welcome to my channel PKS Tutorial, and today I am going to discuss plane electromagnetic waves in free space. Please like, share and subscribe my channel, and don't forget to press the bell icon so that you can get latest updates of my videos. So let's begin. We already know that the electromagnetic waves are the waves in which there is sinusoidal variation of the electric field and magnetic field mutually perpendicular to each other and perpendicular to the direction of the propagation of the wave. Here the time-varying magnetic field gives rise to the electric field and the time-varying electric field gives rise to the magnetic field. So instead of talking about electric field and magnetic field, let us talk about the electromagnetic field. Here the time-dependent electromagnetic field is described by a set of equations which are well known as Maxwell's equation. And there are four fundamental Maxwell's equations, as you can see here. The first one is known as Gauss law in electrostatics, the second one is known as Gauss law in magnetostatics, the third one is known as Faraday's law, and the fourth one is known as Ampere's law. And already these laws you have got in your junior classes. Here the symbols, as you can see, D means electric displacement vector, and rho is the charge density, which I have not mentioned here. B is the magnetic induction, E is the electric field, and H is the magnetic field intensity. Also, J is called current density. The relation between the electric displacement vector and electric field is this, that is D is equals to epsilon times of E, where epsilon is what? It is permittivity of the medium. And B, that is magnetic induction and magnetic field intensity, are related by this equation. That is B is equals to mu times of H, where mu is what? Permeability of the medium. And the relation between the current density and the electric field is this, that is current density is equals to product of conductivity and electric field intensity. Now a free space or vacuum is characterized by these properties, that is charge density of a free space is 0, there is no conductivity, therefore conductivity sigma is equals to 0. Since charge density is equals to 0 and there is no conductivity, therefore current density will be also 0, and permeability of a free space is given by mu naught and permittivity of free space is given by epsilon naught. Now if we put this in Maxwell's equations, we will be getting this. Del dot D is equals to 0, that is divergence of electric displacement vector. Remember, del dot D means what? Divergence of electric displacement vector, and it will be 0. And let this be the equation 1. Again, del dot B will be equals to 0, that is divergence of magnetic induction is 0. Let this be the equation number 2. Again, del cross E, that is curl of the electric field intensity. It will be equals to the negative of the partial derivative of the magnetic induction with respect to the time t. Let this be the equation number 3. Again, curl of magnetic field intensity, or del cross H, is equals to partial derivative of the electric displacement vector with respect to the time t, and let this be the equation 4. Now we will be taking the curl of the equation 3. Taking the curl of the equation 3, we will be getting this, that is curl of the electric field intensity is equals to curl of the negative of partial derivative of the magnetic induction with respect to the time t. And this can be further written in this form. Now since B is equals to mu naught times of H, therefore we can write instead of B mu naught H, and we will be getting this. Again, curl of H, that is del cross H, is nothing but partial derivative of the electric displacement vector with respect to the time t. So we will be putting this here, and we will be getting this. Again, electric displacement vector, if you remember, it is nothing but this. So we can substitute instead of t epsilon naught E, and therefore we will be getting our final expression of this form. And let this be the equation number 5. Now we are going to use a vector identity, and the vector identity we have chosen is this, that is del cross A, that is curl of a vector A is equals to this, that is del bracket close del dot A minus del dot del bracket close vector A, which can be further also written as this. Now this is simply a formula which you must remember. Now using this vector identity, we can write del cross E, that is curl of electric field intensity E. It will be equals to this, which is in accordance with this vector identity formula. Now since del dot D is equals to 0, which we have taken from question 1, therefore del dot epsilon E will be also equals to 0. We have just substituted D with epsilon E, then del dot E will be equals to 0. So we can write in place of del dot E equals to 0, and we will be getting this. And let this be the equation number 6. Now when we compare equation 6 with equation 5, we will be getting this. And this can be also written in this form, that is del square E minus mu naught epsilon naught second order partial derivative of electric field with respect to the time t is equals to 0. And let this be the equation number 7. In the same way, we can take the curl of the equation 4 and we can have this, that is curl of the magnetic field intensity H is equals to partial derivative of the curl of the displacement vector with respect to the time t. Since displacement vector is equals to epsilon naught E, so we have substituted it here and we have got this. Again, del cross E, we know from equation 3, it is equals to minus partial derivative of magnetic induction with respect to the time t. So we have written this here. Now magnetic induction is equals to mu naught times of H. So if we substitute it here, we will be getting this. And let this be the equation number 8. Again, using this vector identity, we can write curl of magnetic field intensity H is equals to del bracket close del dot H minus del square H, which is in accordance with this formula. Here del dot H is nothing but it is equals to 0 because del dot B is equals to 0. So putting del dot H equals to 0 here, we can get this is equals to this. And let this be the equation number 9. Comparing equation 8 and 9, we will be getting this is equals to this, and this can be further written as this, that is del square H or magnetic field intensity minus mu naught epsilon naught second order partial derivative of the magnetic field intensity H with respect to the time t is equals to 0. And let this be the equation number 10. Now let me rewrite the equation 7 and equation 10. So this was the equation 7 and this was the equation 10. Equation 7 and 10 represents the wave equation governing the electromagnetic field E and H in free space. Also, electric field and magnetic field intensity can be written into its component form as such. Now each of the component of the electric field and magnetic field are scalar quantities. Now each of the component of the electric field intensity and magnetic field intensity separately satisfies the scalar wave equation of this form, where U is some scalar quantity, and let this be the equation 11. For example, suppose I am using the component of the electric field Ex. So this wave equation will be of the form this. Also, one more thing is to be noted here, that this wave equation 11 resembles the general wave equation of this form, where V is the velocity of the wave. Let this be the equation number 12. Comparing equation 11 with equation 12, we can write that velocity of the electromagnetic wave with which it propagates in free space is V is equals to 1 by root over mu naught epsilon naught, which is nothing but the speed of light in free space. So this is all in this video lecture about plane electromagnetic wave in free space. I hope you have understood. So with this, I'm just ending my lecture, and if you have any doubt, you can put in the comment section. I will try my best to respond you as soon as possible. So for today, only this much. That's all. Thank you.